Thanks, Brett and Brendan, for awesome talks on chemistry. Now let's take a step back and look at some physical properties. Turns out we don't know some really fundamental properties, say how massive polar planetary disks are, even up to an order of magnitude level. Traditionally, this mass has been measured from dust emissions in submillimeter and millimeter. So basically, we're seeing a continuum emission from dust particles. The problem is dust particles grow in polar planetary disks into rocks and boulders and planetesimals. Once they grow bigger in size, they're no longer emissive in the wavelengths that we're observing. Therefore, we're missing a lot of mass if we only measure mass in submillimeter emission. So turns out 99% of the disk mass is in H2 gas. So ask the question, what about we measure the disk mass directly from the gas emission? The problem is H2 doesn't have electron dipole moment, so it doesn't emit in typical polar planetary disk environments. So this has been done once with HD emission by Herschel. So Bergen and al. They measure the HD emission level. Oops, right here. And then they estimate the disk mass to be roughly 0.05 solar mass, and that's more massive than a lot of estimates made in dust emission. So Herschel is no longer with us, and this line is actually fairly sensitive to temperature, so that's not necessarily a good probe for disk mass. And luckily, we have ALMA. So traditionally, people have been measuring mass of molecular clouds in CO. That's just because CO is the second most abundant molecule in molecular clouds. So that's the first thing people look at when we first got ALMA, when we first became able to detect molecular emissions in those disks. And even though typical commonly observed CO lines from regular CO are awfully thick, we can still observe rare isotope locks, say 13CO, C18O, and C17O, and they could be awfully thin to trace the disk midplane and therefore the entire mass budget. However, to translate our observation of emission to the actual disk mass, mostly in H2, is a very non-trivial process. So first of all, there are different fractionation processes that could change the real CO to CO ratio. And CO chemistry can also deviate the CO to H2 ratio away from the molecular cloud value. So this temperature and density structures, they determine the chemical processes, and they also decide the excitation processes that eventually lead to the emission lines. So our approach is to model the thermal chemistry of evolving polar planetary disks. So we first look at the thermodynamical structure. We follow the evolution of a T-Tauri disk for 3 million years. That's roughly the lifetime of a polar planetary disk around the solar type star. And then we look at kinetic chemistry model. So the model was built upon the UMISS database. We have more than 1,300 reactions, including gas phase reactions, grain surface reactions, and different photochemical reactions to account for fractionation processes. So this is what we found. So now we're seeing a cut of the polar planetary disk. So we're only seeing the cross section. And then the quantity plot here is the number density of the species divided by the total proton number density. So we're seeing the abundance here. And minus 4.2, the right color here, is the input abundance. So red means a lot. And blue means the certain species is depleted. So we're having a lot of carbon dioxide ice, and it turns out that's inherited from the cloud phase chemistry model. However, CO is depleted beyond 20 AU from the central star, and turns out the disk is hot enough for CO to stay in the gas phase the whole time, so that's not due to freeze out. We asked the question, what happens? So if you look at one particular point, in this case 60 AU on the midplane, the black line here is showing the time evolution of the abundance of CO. It drops at a million-year time scale. Same for methane. And instead, the abundance of organic molecules increased, and they pretty much plateaued after 2 million years of evolution. if it averages over the entire disk, it turns out more than 45% in some models, around 45% of available carbon is stored in organic ices by the end of the T-Tory disk evolution. So we asked the question how robust our result is. So we tested our results against different models. So we have, let's see, this is a different chemical network, different input abundances, and different dust properties. So the takeaway of this is we have a lot of carbon dioxide ice, in all cases around 35%, and a lot of organics, roughly on average 40% of available carbon. And the CO abundance is only around 15%. So unless in molecular cloud, we think CO may not be the most abundant molecule out there. All right, so we started this project trying to find out what can we use as a probe for the disk midplane. And it turns out C17O becomes awfully thin after 10 AU from the central star. And for C18O, the number is around 15 AU. So basically that means, yes, we can observe C17O or C18O and use those lines as a direct probe of the disk midplane and use those lines to measure the disk mass. However, because the chemical evolution happens on a million-year timescale, so it turns out the opacity changes quite dramatically as the disk evolves. So now we're looking at the optical depths of CO120 line as a function of radius. So we start with a really flat profile, and then the abundance drops at around 15-20 AU as the disk evolves. And interestingly, this has been seen recently in a CO observation of T-level hydrate. So now we're again looking at the column density of CO as a function of radius. The line is flat if we're only looking at dust emission, but we're seeing a huge drop at about 20 AU, just as what we predicted here in the model. All right. If we take a step back and look at some global properties, turns out people are seeing really small gas-to-dust ratios in polar planetary disks. Just for reference, the canonical interstellar value is 100. And in disks, people have been observing a whole range of values all the way from 10 to 70. So the blue box here is observed data, and the yellow boxes here are our model predictions if people interpret the observation assuming a constant CO to H2 ratio. All right, so back to the question of the global disk mass. So are we actually seeing the gas depletion globally or just CO depletion? So does it mean we're underestimating the gas mass just because CO is depleted? So in order to do that, we model the line emission based on our chemistry model. And then luckily, the CO depletion does have chemical signature in spectral line profiles. So now we're looking at C17O line, 3 to 2 rotational emission for the end of evolution. And the top panel, we're seeing the actual spectra, and then the lower one is normalized line profiles. Because the chemical depletion happens, mostly in the outer part of the disk where capillary rotation, capillary velocity is smaller. So for the chemical evolution model, let's see, how does it work? The inner part is more depleted. I mean, most of emission comes from the the outer part is depleted, and most of the emission actually comes from the inner part of the disk where the capillary velocity is much higher. All right, I know there's a lot of details, so I'll leave the conclusions here and start take questions. Thank you.
I'm going to use my privilege and ask you the first question.
All right.
What is the dominant parameter in your model that determines where the lines go optically thick in terms of AU? I mean, you have a radius out from the central star where they go optically thick. But
yeah.
what part of the model determines where that is?
Oh, we actually compute the optical depth just based on the chemistry. So we have the chemical evolution model. It's actually a 1-point model. So we follow the chemical evolution. It's a 50 by 40 grid. So we follow the evolution for 3 million years for every single point of the disk. And then we integrate to get the optimal depth. Yeah, so that estimation was for a phase-down geometry. We also have other more detailed prediction coming up in the line profile paper.
Okay. Other questions?
So you mentioned that the CO depletion is a result of complex organic ice formation. What's driving that reaction?
That's a great question, and I have a backup slide for that. Oh, that's the network. Just flash it over in case anyone is interested. And so it turns out the reaction time scale is limited by ionization. So for roughly about 20 AU on the mean plane, so this is the key figure. That's the contribution of X-ray ionization. Basically, for red and yellow, that means that's where X-ray ionization dominates. And then in the interior, I would say within 1 scale height of the disk, that's where cosmic ray and secondary UV photons dominate. And that's a great question because Elsa and Pat Bergen's group and Fred Adams, they've been proposing that cosmic rays can be shielded by the magnetic field of the central star or the disk. So if that happens, that will turn down the reaction rate by a lot. So we are testing that situation too. And I'll point you to Elsa's, I think her 2005 paper. So they try to constrain the cosmic ray and cosmic ionization rates by observing, by modeling CO abundance. Mm-hmm.
Hey, it was a really nice talk. Thanks. So do you expect that the timescales of the reactions you're considering are going to be fast enough that the dynamics aren't important?
Oh, that's a good question. So let's see. The timescales for freeze-out and gas phase reactions are definitely not, and for green surface reactions, for green surface reactions, they happen much faster than the dynamic timescale, so they're fine. And I think there is one particular kind of reactions, now I can't remember which kind, that could be relevant. So you might want to consider mixing or transportation for that. But for us, we track the change in density, temperature, and then change of column densities. Yeah, one group, they're trying to combine the, okay, better. And there's one group, we're trying to combine the dynamic and the chemistry together, ProDemo. The code is called ProDemo. So they have, the problem is, so basically they calculate the thermal structure, line excitation, and chemistry coherently. The problem is they only have parameterized models. So in our case, we actually have MRI turbulence in the disk model. So the first paper was based on MRI turbulence. Mm-hmm.
All right, well, thank Emma again.